Hi, welcome to podcast 8.2 on the Slutsky equation, cost minimization, and duality. There's a lot here for you to absorb in this podcast. You may need to watch it twice, so pay close attention the first time. In this podcast, we work on a continuation of understanding income and substitution effects from podcast 8.1. In this podcast, we will do it now mathematically using the Slutsky equation. This equation is very important to economists analyzing consumer demand. It breaks down the changes in ordinary demand system the way we did in diagrams in 8.2, but this time we're going to do it using mathematics. So it's a little bit like taking dynamite to consumer demand when we go from the meticulous operations involved in doing it with a diagram to this quick and speedy methods available to us through calculus and mathematics. We're going to throw off our surgical gloves, put on our revolutionary hats, and blow up demand functions. Before I bring in the TNT, let me give you an overview of the objectives of this lecture. We're first going to define and utilize the Slutsky equation, then derive indirect utility using cost minimization, and in the third part, relate direct and indirect utility relationships to each other using duality theory. So let's get with it, shall we? Here is the star of this first part of our program, the Slutsky equation. The left-handed side of the Slutsky equation is the derivation of our ordinary demand function, x star, differentiated with respect to a change in its own price, piece of x. In other words, we are looking at the change in consumers' demand after a change in price. This overall change in price is the result of two different processes. Remember our movement along the original indifference curve or pivoting of the budget constraint resulting from a price change? That is measured by the first term on the right-hand side of the Slutsky equation here. This first term, dxc over dpx, is the change in compensated demand in relation to the price change. It tells us how the consumer's demand changes when their utility is held constant. The last set of terms on the right-hand side of the equation tells us what the income effect is, or this is also the product of demand x times the slope of the Engel function. Below, we also have in words an interpretation of the different elements of the Slutsky equation. We have, gives us the slope of the ordinary demand function and explains the components of that slope in terms of what part of compensated demand drives the slope of that equation and the slope of the Engel function. The full effect of a change in demand is equal to the substitution effect less the income effect. We can use this information to do what we call signing the Slutsky equation for different types of goods. So here we have, say, a Slutsky equation for a normal good. In the uncompensated case, we would expect a negative slope on that normal good or ordinary normal good type of product. This would be a result of the sum of negative compensated slope and then minus x, which will be positive, plus a positive effect. So we have a negative and then a negative over here gives us a negative for a normal good Slutsky equation. The signs we would expect for an inferior good depends on the type of inferior good. For most inferior goods, we'll expect a negative uncompensated demand curve slope. But this is the result of both a a negative compensated demand curve slope, and then we actually have a positive effect here net. We're minusing a minus. So we have minus, minus, the plus and the minus times each other equal minus. So this is a negative, and then this all together here will be something positive. But if the compensated demand change outweighs that of our Engel curve relationship, then we're going to have a net downward sloping demand curve. But if we have a Giffen good, then positive. So right now I have it as a negative, but it could actually be a positive relationship if the income effect or outweighs the substitution effect. So that would result in an upward sloping demand curve. Rare, but possible. You may be wondering at this point, though, how to derive compensated demand by itself. This is an important tool to be used, understanding compensated demand. Like ordinary demand, we will use the Lagrangian function using an objective function. Unlike ordinary demand derivation, the cost function goes by the objective in the objective function, and the utility function serves as a constraint, so we keep utility constant. And the process of solving for optimal cost minimization is called the cost minimization problem. Okay. Let's consider the following cost minimization problem. Here you will see in the objective function we have what looks like the budget constraint. It is our expenditure M equal to the price of good X times X plus the price of good Y times Y. These are minimized subject to the utility constraint, where we're trying to keep our consumer at a certain level of utility by choosing the correct amount of X and the correct amount of Y to keep their costs at a minimum. As we work with this, we will develop a Lagrangian function. Here it is on the left where we have the Lagrangian, where the first part of the equation is that expenditure function that you saw. And then we have a new type of Lagrangian multiplier. I like to use something different for these types of problems just so they don't get confused with the Lagrangian multiplier we had earlier. So I use mu and then take it times u minus, say, xy, if that is the shape of your utility function. Then the first order conditions will still be taken with respect to each choice variable. So in this case it will be with respect to x, and then with respect to y, and then with respect to the Lagrange multiplier mu. Just like we did before, we're going to take this and try to solve for our Lagrange multiplier as a function of the other variables. So what we do is we set our ratio of prices and the choice variables equal to each other to derive one of the choice variables in terms of the other and prices. This is then substituted into the utility function instead of before we would have done the budget constraint. Now it's in the utility function, and we set this equal to 0 to solve for our first compensated demand. So go through, solve for this, and here I have the compensated demand for X, for X as a function of both the price ratio and utility. Then I can use this expression here, which X is defined as there is the optimal compensated demand, and put it back up here where I had my Y in terms of the price ratio in X. I'm putting this Py over Px times U to the 1/2 into that equation here to solve for the ultimate Y compensated demand. Be sure to go through these steps a few times and make sure you understand the order of them. You'll be doing some of this with your homework problem as well. Finally, at the end, what we can do is take what we had in terms of what our x function was and what our y function was, put it back into our cost function, or what we had as our budget constraint, and then we have what we call indirect utility. Excuse me, that is not right. So what we're going to do now is take those those compensated demand functions and put them into our original expenditure or budget constraint function to get the expenditure function. So here we have our expenditure as a function of the price of x times the compensated demand function for x plus the price of y times the compensated demand function for y. And we can solve it and get a finalized expenditure function. You'll notice now things seem a little bit cooler after blowing them up with the Slutsky equation. One of the things that I feel is most beautiful in economics is the concept of duality, which is a cool, calming type relationship between different types of functions. So here we have the expenditure function, and we got it by working with the utility function. What I'm going to present to you next in duality tells you how you can use the expenditure function to get a utility function and vice versa. So I'm very pleased to talk to you now about duality relationships. And I just want to express a little bit about this photograph. I chose it because I think it represents the beautiful duality of a swimming in life. And while we have these people floating through the water and experiencing the ocean and it moving them, they're also moving the water through the release of their bubbles. So there's a duality in many parts of life, and we get to experience it too in economics as we can look at the relationships between the many different types of functions and how they speak to each other. Roughly, this diagram of duality relationships gives you an idea of how the different types of relationships are between different types of mathematical functions in economics. We started out the semester looking at utility maximization and using it to solve or derive Marshallian or ordinary demand, which we talked about for much of our time. And then this, when we put our x stars and y stars from ordinary demand utilization back into the utility function, we get the indirect utility function. That is a function of income and prices instead of just the goods that you choose. So likewise, what we've just gone through in this last section of this podcast is the expenditure function minimization. When we solve that, we are able to derive the Hicksian demand curves. And then once we have those Hicksian demand curves, we substitute those back into our original expenditure function to develop what we have as the cost function. Now, this can be inverted then to derive the indirect utility function, and get ready for the next slide. There's a lot more tricks we have up our sleeves to be able to go from the cost function to reverse solving for our Hicksian demands, and also for the utility function to reverse solve for our Marshallian demands. We can substitute the cost function into Marshallian demands to derive Hicksian demands, and vice versa, the indirect utility function into Hicksian demands to get Marshallian demands. Whew, that's a lot, isn't it? Here are the two things. If you look back on this slide, I show you that to go from the cost function to getting back and retracing your steps to get the Hicksian demands, we have a tool called Shepard's lemma. And then from the indirect utility, it's Roy's identity that gives us a relationship from that to Marshallian demand. So here's Shepard's lemma at the top. We start out with a cost function, which is a function of utility and prices. If we want to derive back the Hicksian demand or the compensated demand for one type of good, let's say PX, then we would partially differentiate it with respect to PX. In this case, this function is generalized, so I just have it in partial differentiation with respect to PI. And then this is going to be equal to the Hicksian or compensated demand for that type of good. So if we had done this with respect to PX, we would have gotten the Hicksian demand for X. So this gives us what we're going to say is this QI, which is the Hicksian demand for X. Now, if we want to derive our demand in terms of prices and income, what we will do is take this partial with respect to the cost function, which gives us QI, and substitute into this function the indirect utility function, which is a function of income and prices. This gives us our generalized demand function as a function of income and prices. Working the other way, we can take that generalized demand function and substitute into it the cost function, and then we get back our Hicksian demands as a function of utility and prices. And then if we have our indirect utility function and we substitute in the cost function, we have our utility function. If we differentiate our utility function with respect to income, our cost function with respect to price, and our indirect utility function with respect to the same price, then we get back our generalized demand or ordinary demand, and this is referred to, and this is equal to the negative ratio of our partial of our indirect utility with respect to price over the partial of the indirect utility with respect to income. And this is referred to as Roy's identity. So I encourage you to review this process in both this vodcast and through available notes through class and in the textbook. This is an important concept to understand and helps us go through this diagram from our cost function to our Hicksian demands, from our indirect utility function to our Marshallian demands, and so forth. And here is those substitution relationships that are also demonstrated here in the middle of the process. I'm going to leave you with this to mull over. There's assignments on the SmartWorks related to this chapter and to this vodcast. I encourage you to play it again, review it carefully, and be sure you understand the relationships in the Slutsky equation, how to derive the expenditure function, and finally, the relationships defined by the duality diagram and Roy's identity and Shepard's lemma. I look forward to seeing you again and hope you enjoy a relaxing time after this.